Okay, so welcome everyone to the last episode of season 8 of the Isogeny Club. Today we have Ryan Rueger, a PhD student from the TU Munich, Technische Universität Munich. Is that
Yeah, that's
something?
correct. Yeah.
Yeah, okay, thanks. Supervised by Luca De Feo and Lorenz Pani. I also researchers at IBM. So a guy with many hats, and he will tell us about this new really cool Nike called Coral. So please take it away, Ryan.
Thank you, Jonathan, and thank you for Maria for hosting this season of Isogeny Club. Uh, just to say thank you for all of the viewers and all of the previous speakers for having done this and for inviting me here today. So I'm going to talk about Coral. It's a faster isogeny group action for post-quantum Nike. And this is joint work with Andrea, Giacomo, and Sina. Um, so let's begin very quickly with the fundamental Clapoti construction that has been um, central to many important constructions for the last 2 years or so in isogeny-based crypto. And it's an algorithm to compute the isogeny class group action in polynomial time. A fundamental building block of this construction is this kind of two-dimensional um, isogeny construction, which is this proposition 2.1. And it says that if we have some imaginary quadratic order and an O-oriented elliptic curve, and we have some equivalent ideals to some, let's just say some class C, then we can write down this commuting square of isogenies. Here I'm abusing notation, as we often do, right? The A from the ideal is actually the isogeny corresponding to the ideal A. And because A is equivalent to C, we see that the codomain of this isogeny is EC. And it's the same thing for B. There's a small typo. This should be mathfrak C, sorry. And we get this commuting square. And from Carney, this gives us a two-dimensional isogeny from E times E to EA times EB. And where EB, of course, is EC overline, like the conjugate. Anyway, sorry. So this is a very common thing we've seen many times before. And when the norms are coprime of these two ideals, then we can write down the kernel very easily of this higher dimensional isogeny given by this expression. In particular, when n is smooth and the n torsion is accessible, we can actually evaluate phi as an isogeny in dimension 2 to recover EC. This thing here, which is, of course, the action of the class of the ideal A on the oriented curve E. So, sorry, I just realized I was zoomed in a bit much. So this is a fundamental building block. This was kind of a tool that was used by Q Fester in the supersingular setting. This is the oriented setting. And in practice, we don't just want that the n torsion is smooth and the n torsion is accessible, but we actually want n to be a power of 2 and it to divide p plus 1. Right? So when this is the case, then the torsion is actually rational on the curve. It will be fp2 rational. And because n is a power of 2, we have already existing formulae for evaluating 2 to the e isogenies in dimension 2. So that's the fundamental building block that we want to use. And we see that the core difficulty in practice is really just, if I have a class, I need to actually compute these ideals A and B conjugate that are equivalent to C, so they're representatives of this class here. And we want that the sum of the norms is a power of 2, right? So this is something that you don't get for free, but we can think about it for a minute, right? We can recall that the equivalent ideals are parameterized by the ideal itself. So that's a lot of words to kind of say what's written here formulaically, that if I want to write down the set of all equivalent ideals to C, I can parameterize these by multiplying by the conjugate of some element in C and then dividing by the norm of the ideal C. Not only this, right, we also know something about the norms of the ideals that are constructed this way. So if we look at this ideal, we see the norm of this gamma conjugate times C over norm of C has norm of gamma divided by the norm of C. So there's this close relationship between the norm of the element we sample and the norm of the ideal that we end up getting. So just for notation, if we fix a basis of the ideal C, we kind of see that finding equivalent A and B that satisfy this nice property up here is equivalent to finding two different endomorphisms so that their sum of their norms is equal to 2 to the e times the norm of C. I've just taken this norm of C over to the other side. And you look at this and you think, well, okay, this is a Diophantine equation in 4 variables. I want to get something smooth out of it at the end. And maybe if you've done isogenies for a while, you might think in this and see this and think of KLPT immediately. And it turns out that this idea works. You can use KLPT after significant work, right? So first of all, setting up the right curves, setting up the embeddings, rewriting this equation to something that's more meaningful, actually solving, setting up the KLPT instance and solving it. There's still a lot to do, but the fundamental insight, the idea towards the Clapoti with a K paper is kind of on display here. And one unfortunate side effect of having to use KLPT or of using KLPT in this setting is that, as we know, the outputs of KLPT are quite large, right? So if you want to find a smooth element inside an ideal or an equivalent ideal of smooth norm, the norm will be quite large, which in practice means that you have to increase your base field size quite a lot. This isn't devastating, right? This still gives you an efficient algorithm to evaluate, and we'll see some benchmarks later. But it also demonstrates that this Clapoti approach maybe has some limitations. Nevertheless, it's a good starting point to the Coral Nike that I'll be talking about later. Just in a bit of wider context, sorry, I'm having problems with the Zooms. All right, so in a bit of wider context, this is a snapshot of the current landscape in group action isogeny group action algorithms and partially also protocols. So I'll quickly go through this a little bit. So it's sort of sorted by time. So at the top here, things that appeared first in the literature, and down here, things that appeared last in the literature. And we see that, for example, Clapoti was inspired by Clapoti, which alternatively inspired PEGASIS and QT-PEGASIS. And perhaps there's an arrow missing here between Clapoti with a K and Coral because of the previous slide. But we see that Coral is inspired by the original Clapoti construction and a cryptanalytic insight from scale that we'll talk about later. There's not everything here, right? There are other protocols missing from here, mostly things that are more implementation based, but still obviously include interesting new ideas. Anyway, so Coral is down here. It's restricted. So this is why I say it's a fast isogeny group action for Nike, right? For a Nike, you only need a restricted group action. And it comes from Clapoti, which is kind of a bit different to the things that have come from Clapoti beforehand, because the things that have come from this Clapoti with a C, have been unrestricted. Okay, so let's talk about Coral. There's this core observation that is almost the entire idea. It's very insightful, I think. But before we go on, I'm just going to quickly fix some notation. So we'll say the imaginary quadratic order that we want to consider is Z adjoint pi, where pi is the usual Frobenius endomorphism, or it's an algebraic integer satisfying pi squared plus p is 0. And we want the corresponding p to be 7 mod 8, right? This is what's usually known as the Frobenius orientation. And by fixing the 7 mod 8 case, we see that the class groups of Z adjoint pi and Z adjoint pi plus 1 over 2 are actually isomorphic. And that allows us to work with this kind of slightly easier, nicer class group and still act on curves that are on the surface. So from previous literature, like from PEGASIS and QT-PEGASIS, working with these z pi plus 1 over 2 oriented curves, these curves on the surface is quite nice because they have lots of FP rational 2 torsion, and that allows us to compute our isogenies more efficiently. We'll talk about that a bit later. So although I just said that it turns out to be, or it appears to be difficult to sample these A and B ideals that are equivalent, whose norms sum to 2 to the E for some given class, it does turn out that actually there are many classes that are represented by such A and B. Right, so this is not like the real difference here is that for a given class, it's difficult to find the ideals. But if you don't care which class you're representing, it's fine, right? There are many of these, and we can sample them relatively easily. So yeah, slightly more precisely, there are roughly 2 to the E over square root P classes inside the class group represented by these kind of pairs of special ideals whose norms sum to 2 to the E. And we can sample from this set relatively easily by solving a relatively straightforward norm equation. And the core idea behind this norm equation and the core idea behind the sampling algorithm is simply just that if A and B conjugate are equivalent, then A times B must be a principal ideal. So it must be generated by some gamma. And in particular, the norm of this gamma will be x squared plus y squared p, because Frobenius has trace 0. This you don't get any mixed terms. And well, okay, so that's clear from the definition of gamma. But also, if the norm of A plus the norm of B is 2 to the E, then the norm of A is going to be some q, and the norm of B is going to be 2 to the E minus that q. But at the same time, we can rewrite this equation, right? We can say q is equal to some 2 to the E minus 1 minus some A. And then if that's the case, then 2 to the E minus q becomes 2 to the E minus 1 plus the same A. So in particular, we get this slightly nicer expression on the right-hand side. So what's in like magenta here, pink, red, is the kind of norm equation associated to finding these gammas. In practice, or in fact, actually, the converse of this construction is true. So if you have a solution to this norm equation, so if you have some x, y, and a satisfying x squared plus y squared p equals to 2 to the 2e minus 1 minus a squared, then you can write down this endomorphism gamma here, and we get two equivalent ideals of this shape, whose norms are 2 to the e minus 1 minus a and 2 to the e minus 1 plus a. So in particular, the sum of their norms is 2 to the e. So yeah, so you can see how from a solution, so if you have a pair, it's at the generator has this property, but also any solution to this norm equation gives you a generator, gives you these ideals that you can sample from. So this quite immediately gives you an algorithm to sample from these pairs of ideals, or to sample classes which are represented by pairs of ideals whose action can be computed in dimension 2 using the two-dimensional Clapoti construction that we spoke about at the very beginning. So the core idea is, as it's very common in like norm equation solving techniques, is to guess one variable and then hope that the rest kind of works out. So we can guess some y, we even sample some odd y, and then we try to decompose this quantity here, this Ly, as a sum of two squares, right? And when P is 3 mod 4 and Y is odd, we see that this left-hand side is 1 mod 4, which is already a good sign, if we recall that to decompose an integer into the sum of two squares, this can only happen if every prime that is 3 mod 4 that divides our number divides it with even multiplicity. So if this, for example, if Ly is prime, we know that it is the sum of two squares. And in fact, we can compute it fairly efficiently. And so in particular, when Ly is prime, we can find a solution to the norm equation up here. So as I said, from the theorem that tells us that when that characterizes when a number is the sum of two squares via its decomposition into primes. So the theorem theoretically says this, but also in practice, we need to know the decomposition to do it, to actually compute the decomposition. So we simply use some trial divisions and compute some partial factorizations of this Ly on every y sample to try and decompose Ly to the sum of two squares. So kind of informally, what we do is we sample some odd y, we perform some trial divisions by a small set of bad primes, right? So these bad primes are the ones that are 3 mod 4. And if when we do the trial division, we see a bad prime divides our Ly with odd multiplicity, we immediately reject and we sample a new y. Else we continue. We then do trial division by some good primes, right? So maybe we want to compute a partial factorization because at the end we need to know the full factorization of the Ly. So we do some trial divisions even with good primes. And then when that's done, we will know that our Ly is somehow this shape, right? It will be, because we didn't reject, we know that the product of the bad primes must be with even multiplicity. There will be some good primes potentially that divide Ly, and then there'll be one final number, which I've called L prime question mark, to kind of make up for the rest of the factorization. And then we do a primality test, and if L prime question mark is not prime, then we just resample and go back to step one. If it is prime, if Ly prime, if L prime question mark is prime, then we know a full factorization of Ly, and then for all of the prime factors, we can go through and we can decompose those as sums of squares using Konakia's algorithm, which is like a factorization in the Gaussian integers. And after we've computed the sum of two squares for each individual prime, we can combine these back together to obtain a solution for the entire Ly. So yeah, to be a bit more specific, the good primes we can decompose into the sums of two squares using Konakia, and then the bad primes appear with even multiplicity, so we can just multiply these into x and these into a to obtain a solution for x squared plus a squared equals Ly. For reasons that we'll see in a minute, it's good for a to be odd. So if a is even, we just switch x and a, right? Of course, if x squared plus a squared, yeah, we can choose which one's which. And because this Ly quantity up here is 1 mod 4, we know that one of x and one of a must be odd. So we can just choose a to be the odd one. This is a priori an arbitrary choice, but we just enforce it this way. It's worth noting at this point that in SkiSign, I think, or potentially previous versions of SkiSign, when solving norm equations, it turned out that doing these trial divisions wasn't very helpful or like didn't speed things up. It was just easier to write down, to pick a random y, well, in this context, to pick a random y, and then just see if this Ly quantity was prime or not. But in the context of Coral, where we have much bigger primes, the probability of Ly being prime is much lower, and so trial divisions really make a lot of sense. So from some quick testing and or at least from our implementation, it was clear that if you don't do trial divisions, the entire algorithm will be maybe 5 or 10 times slower, maybe even worse at larger prime levels. I can't quite remember. So anyway, if someone's looking at this and thinking, well, why are you doing trial divisions? This wasn't helpful in SkiSign. Just to remember that in SkiSign, the primes are much smaller than in Coral. So after you've sampled an ideal, you want to then actually compute this higher dimensional isogeny phi, this two-dimensional isogeny phi. And if we recall from the construction, and I mean, I know this is a lot of notation, but the idea was that this x, y, and a immediately gave you these two equivalent ideals, a and b, as written here, right? They were equivalent, and they had the norms 2 to the e minus a and norm 2 to the e plus a. And from this quite concrete expression, we can write down the kernel of the higher dimensional isogeny, which is given by 2 to the e minus 1 minus a times p in the first coordinate and xp plus y pi p in the second coordinate. So this is not magic. This is just following what the original construction said. And we see immediately that if our prime is of the usual HD friendly type, right? So if the prime is like a large power of 2 with a small cofactor plus 1, then this 2 to the e torsion should be rational, and then we should be able to write down this kernel. And because 2 to the e is smooth, we can break up phi into an isogeny chain of length e. So that's not particularly my thing, but what ends up being quite interesting is that when your prime is this HD friendly form and your elliptic curve is on the surface, namely it's z pi plus 1 over 2 oriented, then we can sample a basis p and q of the 2 to the f minus 1 torsion whose x coordinates are fp rational, right? Or in other words, you can sample a point on the curve, an fp rational point on the curve of order 2 to the f minus 1, and a point q on the twist of order 2 to the f minus 1. And when you do that, when you choose a basis of this in this way, when you choose this way to represent the kernel, then this expression up here becomes even more simplified. Right? So Frobenius of p will just be p because p is a fp rational point, and Frobenius of q will be minus q because q is fp rational on the twist. So in particular, we get this very explicit representation, kernel representation of we get a very explicit description of the two-dimensional isogeny looking like this, right? So this is really just point multiplication and again point multiplication in the p point and again point multiplication in the q point. Now there's a small subtlety going on here, or like a small detail, that when we sample this basis, we're kind of the algorithms that we usually use, at least the one, for example, that's in PEGASIS, the one that we ultimately implemented. This algorithm only allows you to sample a torsion basis of order 2 to the f, but we need a torsion basis of 2 to the e, so we need to scale down the points p and q to some p prime q prime. There should be a q prime equals here. Sorry. An immediate question is as well, like, can we get away with this, right? Is there enough two torsion? And we'll see later on that there's comfortably enough two torsion because we're simply targeting a like. But I'm getting ahead of myself. So the key point here to take away is from this norm equation solution, x, y, and a, we can write down the ideals corresponding, the corresponding ideals, which are equivalent and have norms that sum to 2 to the e. You can write down the kernel of the Carney map in dimension 2. And in fact, when you sample a basis in this nice way, your kernel description is very nice. Also, later on, we'll see that you can work the majority of the isogeny computation will be over FP. And that speeds up computation significantly. So let me move on to the kind of security analysis of this sampling algorithm, right? So we said we're going to sample some ideals and how are they distributed in the class group? Are there enough of these? How large does the E need to be in the 2 to the E parameterization so that we get enough, so that our key space is large enough? And so this is There are some fairly large heuristics in this argument, but also, as I'm told at least, heuristics that are not too uncommon when working with the class group. So the first kind of observation is that if I write down an ideal IY, or if I have an ideal coming from our sampling algorithm, namely an ideal coming from this X, Y, and A norm equation solution, this ideal will represent a class C, or the equivalent to an ideal C, if and only if the norm form of that class represents both 2 to the e minus 1 minus A and 2 to the e minus 1 plus A. I feel like that direction is fairly clear because precisely our sampling algorithm gives us these two pairs of ideals, right? The ideals that we saw here. We know that, of course, the norm form of that class must represent the norms of both of the ideals. But the converse is also true, right? If the norm form of a class represents both 2 to the e minus 1 minus A and 2 to the e minus 1 plus A, it means that the conjugated product of these two equivalent ideals will be an endomorphism whose norm is of the shape q times 2 to the e minus q, and therefore it will be a solution to the norm equation that we originally set out to find. So it sounds a bit circular in a way because it is, but the point is that we can tie the representation, the representatives of a given class to the norms represented by the class's norm form. And that's useful because at least to support a theoretical argument to support why we believe the distribution of our ideals is uniform in the class group is this result from Blomer and Granville. This paper here talks about different asymptotic behaviors of representations of binary quadratic forms. And in particular, it has this result when when x, this quantity x, is exponential in the discriminant, then the number of the integers represented by a given class less than x is asymptotically equivalent to x divided by the square root of the discriminant. That's a lot of like technical stuff to say. The important thing is that the implied constants in this asymptotic equivalence do not depend on the class C. In other words, every single class in the class group has asymptotically the same, represents asymptotically the same density of numbers less than x. Or in other words, every class, the norm form of every class represents roughly the same number of numbers. So now we can try and combine this. So no individual class is somehow special, and because no individual class is special, we hope that we don't land in one of these class in a potential special class more often. We can't because there are no special classes. So we kind of try to make this more rigorous with the following two heuristics. We assume that q and 2 to the e minus q behave like random integers that are 1 mod 4. Now, I'm sorry, this was in a previous slide, but this quantity q is just this quantity here. There was this change of variables between a and q. So these two numbers we expect to behave like random integers that are 1 mod 4. That's a heuristic assumption we make, and you can either believe or you can't. We did do some experimental analysis that I'll talk about a little bit later to back up our claims. But this heuristic is an important tool that we need. And the second heuristic is that the events that one of these numbers is represented by this norm form corresponding to a given class, that these two events are independent. And maybe that makes sense. I mean, maybe that's like if this class does not represent this integer or does represent this integer, I don't see why it should represent this integer any more or less based on whether it represents this integer or not. At least that's what the heuristic is saying. And now, with these two heuristics together, we then can conclude that a uniform random choice on the y that we make, and then the resulting solution x and a in the entire normal equation solution, that this uniform random choice on y makes the ideal distribution inside the class group uniform. That's slightly hand wavy, I agree. There's at least two heuristics on the screen. But we experimentally tested this hypothesis up to primes of size, I think 64 bits. Of primes of those sizes, we can do the sampling algorithm fully, right? We don't need to hope that the last prime factor. So for example, if I quickly go back here, we could just factor this number Ly fully and then find solutions, all of the solutions to the normal equation. And we saw that the number of collisions was very low, and we could even compute the parameters to ensure that the collisions would be very low. So actually, I think that's the next slide. If we want to estimate, so if we are happy with the argument that the distribution inside the class group is uniform, we still need to care about how big the support is, namely how many classes do we actually achieve. And if we look at this quantity Ly, we see that it's of size roughly 2 to the 2e, and so it's primed with probability roughly 1 over e. So because I'm sampling y from this range between 0 and 2 to the e times divided by the square root of p, then I would expect to see at least this many ideals, right? This many y give me a solution, at least mathematically. Whether I can factor the Ly and find the solution is another question. Excuse me, sorry, that's the whole point. Because Ly is prime, I can factor Ly, and therefore I can find the solutions. But in practice, we find many more solutions than this because we do these trial divisions. And in fact, experimental data shows that we find of all of the solutions that do exist mathematically, we find roughly a fifth of them, even at 4,000 bit parameters, because we can do very aggressive trial divisions because they're very cheap to do. So in practice, this means that the E that we pick, if we want to have a key space of size 2 to the lambda, can be roughly half log p plus lambda plus some small epsilon, accounting for the loss here of this division by E. Right, because if E is of this size, then there are Y will be of this size, and therefore we will have this many ideals that we sample from. The experimental analysis that we did with the collisions, and you can apply like standard coupon collector statistics to how collisions work for an independently uniformly distributed random variable. And you can also compute the min entropy of the distribution inside the class group. We could choose concrete parameters where E has these concrete values. And they hover around this log p over 2 plus lambda. In this case, lambda is 128, if you want to have 128 bits of classical security. So immediately, those who are perhaps a little bit more familiar with PEGASIS will see that in PEGASIS, to compute the action of a random element in the class group corresponding to, for example, 1,000 bits, you would have to compute a 2 isogeny in dimension 4 of length of roughly 1,000 steps. Whereas in Coral, we can get away with a shorter chain because we using the trick or the idea from the scale paper that says that the key space can be much smaller than the entire class group. So I'll get onto that into the next slide. But one important takeaway here is that we can pick the same primes as PEGASIS or as Qt PEGASIS or as any HD-friendly style prime And because we can pick exactly the same shape primes, we can mix PEGASIS, QT-PEGASIS, and Coral together in some protocols to make more advanced constructions or to accelerate more advanced constructions. So I hinted at that a second ago. So in scale, one of the important points made, so scale is SQALE, this paper from 2022. Here they argue that a quantum attack against a class group inversion problem would have to attack the entire class group. So you can have a very large class group, but you can still pick your key space to be exponentially large, but still much smaller than the size of the class group, if that makes sense. So if we just quickly remember, the quantum attack coming from Kuiperberg's algorithm is sub-exponential, and it has to attack the full class group. So we need to make sure that the full class group is very big. But classical attacks, which can attack just the key space, just require that the key space be exponentially large. And this is kind of an important takeaway from the scale paper, and they use this to implement a much more efficient variant of CSIDH. And one property of all of the exponent vector style class group actions, so essentially the entire CSIDH family, and their key space is trivially decomposable into the product of two sets, right? If your key space looks like this as products, smooth products of elements in the class group, then I can kind of, like on a bike lock, I can guess the first half and the second half independently and do a meet in the middle attack on the key space. So they need to have a key space of size 2 to the 2 lambda, where lambda is the security parameter. But in Coral, that's not the case, right? In Coral, one way of seeing Coral is also kind of an exponent vector choice, but you already have exponentially many choices in the first G1. In the first ideal, you pick one ideal, and there's already an exponentially large choice. Right? Recall that when E is of size log P over 2, we have roughly 2 to the lambda ideals to choose from, and that's already enough. We don't need to do an iterative action like one needs to do in the CSIDH family. So in particular, the key space doesn't obviously decompose into the product of two sets, and you don't need to do, you're not susceptible, at least we don't think that Coral is susceptible to meet in the middle attacks. So we can choose the choice that we made before, this E being log P over 2 plus lambda, that this is enough, right? We don't need to have a 2 lambda here because the key space only needs to be of size 2 to the lambda. So with lambda of size 128, we see that E is much smaller than this F, or is much smaller than log P. So we absolutely have enough torsion. And for log P larger than 1024, we immediately get a choice that's compatible with the constraints that we computed from the min entropy of the distribution. That's a lot more technical, so feel free to read the paper once it's online. And so the point here is, for the 512-bit parameters, we needed to make some slight tweaks to the size of E, but it was also smaller than log P. And the advantage, as I kind of alluded to earlier, is if you have a small E, you have a shorter 2-dimensional isogeny chain, and it makes the multi-precision integer arithmetic in keygen much cheaper, right? If you have less words that you have to shift around when you're trying to solve this norm equation, because the size of the integers that we're dealing with here are of size 2e bits. Smaller e, smaller numbers, faster keygen. So having said faster keygen, I can now show you some implementation results. So this is just a comparison of different isogeny-based schemes, where our starting point KLaPoTi is at the top here. And here we have the unrestricted group actions at the top and restricted ones at the bottom. And we see that Coral is quite competitive in comparison. So the assembly optimized 512 bits implementation, for example, is about 5 times faster than the original CSIDH implementation, which is quite cool. And in particular, the 2000-bit instantiation, which with current knowledge appears to be somewhat quantum safe, beats out all of the competition. Except at 4000 bits, there's a slight inversion. So these new implementations, these highly optimized AVX accelerated new implementations of Mark Huben's Nike, that are very, very recent, like 2 or 3 weeks old, I think. At least on ePrint, they've been around for 2 or 3 weeks. At 4000 bits, they perform better than Coral. So there's a couple of reasons for this. One of them is that Coral is written in pure C and is not using AVX assembly optimizations. Another reason is that Mark's Nike scales much nicer for larger primes. If you recall, Mark's Nike has a base prime size of 256 bits, and that doesn't grow with the size of the discriminant, namely with the size of the class group. So the cost of arithmetic stays constant for larger parameter sets. We hope that a assembly optimized or even AVX accelerated implementation of Coral could then again be competitive with these implementations. It's worth noting that there's actually quite recent work, I think, that's not public yet, question mark, on accelerating SkiSign using AVX extensions, and they achieved a nice 3 times speed up roughly, I think. But maybe wait for that to be fully public before you start betting on what's going to be fastest. One point that's worth noting that I will come to in a minute, but let me talk about something else first, sorry, is just the overall Nike performance. So originally I said, oh, smaller E gives you smaller arithmetic and faster keygen. Well, faster is a relative term. Keygen is still fairly slow. So solving this norm equation is quite expensive. And especially at larger parameters, this really kicks in. The asymptotics are not great. We think the asymptotic is roughly cubic so the asymptotic cost of keygen is roughly cubic. And when I say the asymptotic cost of keygen, I really mean the norm equation solving part. The isogeny part of keygen is of course the same as in the shared key derivation. In our defense, if we had to defend ourselves, so to speak, a Nike is often used for long-term secrets. For long-term, Nikes usually have long-term secrets. Ephemeral Nikes could be replaced with chems, for example. And so having a longer keygen is maybe okay. And also, this is kind of funny. So we kind of, for fun, benchmarked how slow RSA would be, like RSA keygen. And RSA 4000, RSA 8000 is roughly as slow as Coral 2000. So I'm not sure if that's a selling point, having keygen that's as slow as RSA, but at least it illustrates the point that RSA is widely deployed, and that slow keygen is apparently acceptable in those deployments. Just also in comparison to some other post-quantum Nikes, because the new implementations of Mark's paper are so new, I didn't have time to benchmark keygen separately from shared key, and also to fill in this table completely. So we're going to compare to DC-Tide, which was the previously fastest post-quantum isogeny-based Nike, which had a very small public key, the same public key size as Coral, at 2000 bits, of course. So Coral is faster there, fortunately. It's worth noting that, DC-Tide is also assembly optimized. And in comparison to Swoosh, which is a lattice-based post-quantum Nike, Coral is much, much slower, like roughly 100 times slower. But for that, the public key is roughly 1000 times smaller. So I would argue on average. No, I'm not. Okay, I wouldn't argue that on average means that Coral is faster. But a fun anecdote, perhaps, is that just transmitting a public key of this size over the internet will also take quite some time. So I think it was like 25 milliseconds or something to just transfer a swoosh public key on a 64-bit internet connection. Sorry, 64 kilobit internet connection, which is 10 times longer than it takes to do the actual derivation. Of course, serious cryptographers who know what they're talking about will know that's acceptable in practice. But I thought it was a fun anecdote, nevertheless. So one short note before closing out on the status of the implementation of Coral is that so keygen I'm not going to talk about here, but I mean just the group action evaluation is kind of constant time, and I know that doesn't sound great, but many of the steps of building blocks are already there, and that kind of is interesting because for CSIDH, constant time implementation was a large challenge, right? Because of the iterative nature of CSIDH, this makes it susceptible to fault injection attacks or even just very simple timing attacks. This doesn't seem to be the case with Coral. So most of the ingredients seem to be here. So the evaluation algorithm consists of basis sampling. That doesn't need to be constant time because it's on public data. And then you do some point multiplications to compute the kernel. That can be done in constant time quite easily. Then a detail that I haven't talked about yet, but there are some diagonal isogenies before gluing in dimension 2. And that's a bit unfortunate. So these are kind of parallel one-dimensional isogenies between products of elliptic curves. And then at some point, the gluing happens and there's the full two-dimensional isogenies. So each of these three ingredients is constant time by themselves, but they leak the number of diagonal isogenies, and the number of diagonal isogenies is just the two-adic evaluation of the sum, something like this. It's roughly the sum of the solution to the norm equation, a signed sum, let's say, x plus y minus a. And it's not exactly clear how you would turn knowledge of this into an attack. But in practice, you can bound the two-adic valuation during keygen. You can just reject when this number is too large for your liking. And also just on average, this number is quite small. So the two-adic valuation of this quantity, if you don't do any bounding, is roughly 2 or 3. So that is not to say that our current implementation is constant time. There's still work to do, of course. But it is to say that perhaps in comparison to CSIDH, hopefully there's less work to do to make this a constant time evaluation. Keygen is a whole different story that we can get into in the questions, but that's not what I want to say here. So thank you, Ray. So there's one more cool application. So earlier I mentioned that the primes are compatible with PEGASIS. We can choose the same primes as in PEGASIS. And because of that, we can maybe compute some actions with Coral, then some actions with PEGASIS. Coral is restricted, PEGASIS is unrestricted. And that can be kind of cool. Like, so for example, in a classic CFISH style signature, you can sample your own secret ideal. So you can, because you sample it yourself, you can use Coral to evaluate that action. You also sample the commitment isogeny yourself. So you can sample that ideal and compute that in dimension 2. And when the challenge bit is 0 or 1 or whatever, when the challenge bit asks you to reveal your commitment, the verifier can also compute this in dimension 2. It's just then if the challenge bit is to reveal CS minus 1, like the other isogeny, then the verifier would have to compute this in dimension 4 because the product of two Coral ideals, two ideals that can be computed in dimension 2, cannot be computed in dimension 2 unless you compute it sequentially. And if you compute it sequentially, you would be leaking your secret key. So this would mean that computing the signature would be much faster because you can use Coral in dimension 2. It's just verification could be slower. Having said all of that, there's ongoing work right now to get a two-dimensional representation of this isogeny here as well, and then you can have full two-dimensional signing and two-dimensional verification. You can get a two-dimensional representation of this isogeny here, spiritually at least, for the same reason that you can get two-dimensional verification in key-sign. You know the public key, you know the endomorphism ring of this curve here, and therefore you should be able to prepare a two-dimensional representation of this isogeny. As the signer, of course. So yeah, quick outlook, just a better understanding of the distribution. They're from this Blomer-Granville theorem. There are some implied constants. If we had a better understanding of those, we could bound the probabilities of hitting a given class better. In other words, to understand the support and the distribution of the distribution better. It would be nice to have a full constant time implementation. I mentioned very briefly that if you sample the basis in this nice way, you can do most of the computation over FP. As in PEGASIS, our gluing and splitting is over FP2. It's just the generic isogenies that are over FP. The diagonal isogenies are a bit of a mess as well because we have to switch to the Weierstrass model. These things can be cleaned up. So that would be nice. That would give a couple of percentage points of improved performance. And finally, there's an interesting question: what other protocols can you accelerate with Coral? Does that work more generally? And that could be applied to this NIST threshold call, where there's the interesting new protocols being made there, and accelerating those would be cool. So thank you very much. The paper should be an ePrint within the next couple of days, hopefully, and I'm happy to answer any questions.
Thank you very much for a great talk, Ryan. As always, please feel free to unmute yourself and ask questions or type them in the chat.
Hi, do you hear me?
Yeah, hello.
Hi, thank you for your talk. I have a question. At the beginning, there were some map with all the Clapoti, for all the protocol, etc. Some overview of all the.
Yeah. This.
Yes, exactly.
Yes.
On this, you put Coral in the ordinary rectangle. Or maybe I'm mistaken, but oh no, ordinary is on the top. Okay, it's okay. I was wondering because I thought this during the entire talk, and I was sure it doesn't apply to ordinary, but okay. My mistake. Sorry.
No worries. It's a good point. The graphic is not perfect. Yeah, it's in the restricted box. There are many boxes.
Oh yeah. Okay. Yeah. Thanks.
Yeah, no worries.
So I have a question about constant time keygen.
Yes, please.
Is it better or worse than PEGASIS, or is it? I guess it's either better or the same.
The flavor seems to be similar, right? There's some trial divisions. I mean, it's a good question. I couldn't tell you if there's like an obvious reason why one should be faster than the other. But the flavor seems to be similar, right? It boils down to, I think, doing some trial divisions, guessing some values, and then trying to Konakia the rest.
Yeah, because indeed it's just solving some norm equation, which is the same problem that we have in ski sign, except now the prime is just really large.
Yeah. So
then,
actually, I'm sorry.
Yeah, so I guess it indeed has to do with the probability that a random guess yields a solution.
Yeah.
And how large this is. Because indeed, like once you fix the size of the prime, then yeah, testing whether a given solution. Well, like, oh, no, that's not true. Okay, sorry, I'm rambling. But
okay, so I have a partial. There is a point that I have a partial answer or a caveat to say is that if you recall this this Ly value here is of size 2 to the 2e, right? So in practice, it turns out if you set e to be roughly log p, so like the maximum torsion you can get, then you do cover an exponentially large portion of the class group. So your key space is very, very large. And then also this number here is roughly of size p squared. So you're then trying to solve a norm equation of integers of size p squared, whereas in PEGASIS it's of size p. Now, in practice, in Coral, when we choose the smaller key space, when we choose e to be log p over 2 plus lambda, then this Ly thing here is roughly of size p plus lambda in bits. Sorry, log p plus lambda. So it's slightly bigger than p, and therefore the cost is slightly larger a priori, like the integers are just bigger, but it's not as big as it could be. So this 2 here is kind of an important thing, but you can get away with killing this 2 by having e to be roughly half log p.
Mm-hmm. But is there some additional thing where to try to increase the size of the key space, you kind of have to do more trial divisions?
Yes. So what is true is that when e is larger, so if we quickly go here, so like the probability that this Ly is going to be prime is directly proportional. Well, it's in relationship to e like this, right? It's 1 over e. So as e grows, this is less and less likely to be prime. I can't immediately tell you if that makes Ly more and more. So if you want Ly to be really prime, like you don't do trial divisions, then it's clear that as e grows, it becomes more expensive to even have an Ly which is factorable. But yeah, actually let me take that back. Yes, as I mean the growth of the algorithm is roughly cubic as we analyzed it, and it's cubic in e. It's really e. Actually, that's a good point. That's also a point to mention here that this is all fixed size arithmetic, right? Once you choose e, then your Ly will be of some fixed size, right, of roughly 2e bits, and then x and y and everything will be of fixed integer size, which, as I understand, is not the case in SkiSign, which also is one thing that makes constant time implementation in SkiSign much harder. Another point to mention in comparison to SkiSign is that the norm equation that we solve here, we do once, and we do it in such a way that, for example, if you reject a Y sample, you don't leak anything about the secret key. There's no, it's just when you do these trial divisions and when you do the chromality check. I don't know. I mean, there's still things that one needs to watch out for, but yeah. Sorry, now I'm rambling.
Yeah, I get it. So indeed, you don't really have to do constant time Kornakia.
Well, you still do, because at the end, right? Where was it? The little description of the algorithm. Yeah, like you do still need xi and ai to be like that will end up being your secret roughly, right? So if
that's right. Okay.
If Kornakia here somehow leaks all of your bits, then that's game over.
Yep. Okay. Thank you.
Yeah, no worries. Yeah, sorry. Like in SkiSign, you need to solve a norm equation every time you do a signature, and therefore the norm equation is somehow bound to prior secrets. Whereas here, at least these phases, at least this bad rejection phase, you can just do and reject, and it's fine. You don't need to worry too much. It's just that if it passes all of the trial divisions, then so yeah, it's good to do this in constant time, definitely. So it's a slightly different flavor.
I also had a small question on constant time, but it was to do with the diagonal isogenies.
Yeah, go ahead, please.
So I guess my question is just, can you just choose to not do diagonal isogenies, or does this affect the probability of success a lot?
It's a good question. So I think in KLaPoTi you could get away with just saying I refuse to do diagonal isogenies and just say that. Unfortunately, in Coral you always have at least one diagonal isogeny, and this just shakes out from the 2-adic valuation of this value. Whatever I said it was, like this valuation is always going to be bigger than 1. For reasons that I can't tell you immediately right now, but it's in the paper. So yeah, there's always one diagonal step. But you can, for example, force, I mean, during keygen, you can say if there's more than one, I reject. And roughly experimentally and also kind of intuitively, the probability of having k diagonal steps is 2 to the minus k. So if you say, okay, I really just, or 2 to the 1 minus k. So if you say, I really just want one diagonal step, then you are rejecting half of the secret keys you sampled, making keygen twice as expensive, and the heuristics on the distribution even more spicy, let's say. But I mean, okay, yeah.
Yeah, I see. But then I guess the question is like, however you would make this constant time, is it going to be more expensive than just rejecting half of the samples?
Yeah, I mean yeah. So you could say I reject more than 16 diagonal steps, right? So the probability of that happening is like of having 16 diagonal steps is 2 to the minus 16, so it's fairly small. I reject, let's say, 0.5% of all of my keys. So the keygen is unaffected roughly. And then you could, and this is ever so slightly unclear, but actually no, let me take that back. It is clear that you could just leak up to these 16 bits of your secret key and then just increase your key space accordingly. So you could, the thing that's unclear is actually you probably leak a lot less than 16 bits. It's probably log 16 bits. And even then it's not clear what you gain from knowing that there was 4 diagonal isogenies.
Yeah, I see. Cool.
Yeah, thanks.
Maybe I could also ask a question right at the end.
Sure, yeah, please, yeah.
So I'm a bit curious for this type of signature scheme where, on the one hand, you have CFish, which showed how to make a signature scheme out of CSIDH by getting a full efficient group action. But also you have something like this C sign, I think it's called, where you do some kind of rejection sampling.
Yeah.
Instead. Of course, it sounds very hard to do this with Coral, but did you think about it at all, or
you mean like a rejection sampling based variant?
Yeah, or do something. So concretely, I was wondering if E was sort of small enough. So probably you might have to do a bit of overkill on the size of your prime, but could you not get like a two-dimensional representation if S and C, these ideals are both, gives you like a two-dimensional isogeny of length E, then could you not get one of length 2E for C times S inverse, for instance?
Yes. So
This was what you mentioned. Maybe
on the geometric side, I completely agree. Like, I mean, yeah, you have the composition of two to the E isogenies. You should be able to somehow. But I think the problem there is how do you algebraically encode that? Like what ideal do you give that doesn't? So okay, you could give both ideals separately, and then you're giving away your secret key for free. And one nice feature from the security perspective of Coral is that these ideals are not closed under products, and they're not closed in any way. Like taking an ideal that is kind of a 2 to the E ideal and timesing it by another ideal that's a 2 to the E ideal. There's kind of no reason why that should be a 2 to the 2E ideal. So as you're saying, if your prime is huge, then actually it's just unlikely that these classes, the product of these two classes lands in the class of in the set of classes which is represented by a 2 to the 2e ideal. But even if it's not, even if your prime is small, and it happens to be the case that the product like CS minus 1 represents a class which would permit this kind of representation, this 2 to the 2e isogeny, it's not clear how you would find this other than going into dimension 4.
Okay.
So I mean, if you want to stay in that, so it's not clear how you would stay in dimension 2 purely using the kind of choral style trick. It seems to me that like preparing a 2-dimensional representation is kind of the quote unquote obvious way to go. And then the verifier can verify this way.
Yeah. I mean, it's also, I guess that's the best you can hope for. That's what you get this way, actually.
Yeah.
Oh, that's nice. Okay.
Yeah.
If there are no further questions, then let's thank Ryan again. And yeah, that was it for season 8 of the Isogeny Club. Thanks to all speakers who have given talks this semester. And of course, some of you might already know, but there's also going to be an affiliated event at Eurocrypt. We will send out a bit more information in the coming days. But for those of you who are also coming to Rome, see you then. Yeah, thank you.